Well, thank you, and I'm very glad to be here. So, first part of this talk, I'll be talking about Mars, and then talk about implications for methane and ice on exoplanets. Well, in contrast to today, Mars, which is pretty dry desert world, which is Mars. In the past, Mars was a quite different place. Has an abundance of fluvial features in these ancient networks, ancient terrains in the southern highlands, alluvial fans and deltas and lakes and modified craters and possible ancient ocean shorelines, suggestive of perhaps an active hydrologic cycle that may have operated in the past. All of this is consistent with a once warmer and wetter planet. However, the most impressive fluvial features, probably by far, on these ancient terrains that are about 4 billion years old, are the valley networks. They often run for hundreds or to thousands of kilometers long and can be several hundred meters to up to a kilometer so deep. A lot of these are actually on the scale, and people don't realize this, about the scale of the Grand Canyon in size. And we have these nice plots from our recent review paper earlier this year showing the Grand Canyon against a couple of Martian examples of valley networks. So all of this suggests that really large amounts of water were required for their formation, suggestive of a warmer climate. And we argued in this paper that cold icy scenarios for Mars cannot produce the water required to form these features. Now, so that looks all good and dandy. The difficulties come, though, with the modeling. The climate models have had a lot of difficulty trying to show how this warmer scenario could have worked. It's been typically assumed that the dominant gas is basically CO2 for an early Mars atmosphere with maybe some water vapor. So let me just illustrate the problem. So on the y-axis, there's surface temperature, and the x-axis is surface pressure. If you have basically a CO2 atmosphere, the highest temperature for the time which we think early Mars was warm, about close to 4 billion years ago, the highest temperature you can get with a CO2 atmosphere is about 230 K and about 2 or 3 bars total. You just can't add any more. If you add more CO2, you will not get additional warming. And basically, I'll talk about this a little bit later, but the atmosphere will collapse, and CO2, just will not give you any more net greenhouse effect. So this is really, really like the faint young sun problem for Mars. This has been the big issue. How did this happen? How did you get water to be stable on the surface? 230 K is definitely too low of a temperature, and you want it to get above the freezing point of water, and that's obviously not there with just CO2. So I think that's motivated a lot of these alternate scenarios that maybe you needed a cold climate. You could form these features in a cold climate. Maybe Mars was never warm. You had all these hypotheses of an icy, cold Mars from various investigators over the years. But just again point to our review paper where we discuss the geological and climatological evidence that we argue that none of these ideas really can explain the evidence, and why a warm and semi-arid climate probably best explains what happened on early Mars. And this is really one issue that I wanted to point out, which will lead into my methane discussion. An icy and cold early Mars is really hard to warm because ice is pretty reflective, and so you're getting a lot of energy that's not being used to warm the surface. It's just being reflected out to space, and the more ice you have on the surface, the more greenhouse gas you need to make up for that deficit. At higher surface albedo, and I have these plots here with the arrow, to achieve a given surface temperature, you need to increase, as you increase the ice and increase the surface albedo, you need to go to higher and higher pressures to get the same surface temperature. And in fact, if there's too much ice in the surface, there's a point beyond which you can't warm the planet at all, and it just collapses. The atmosphere collapses entirely. So this is what I deemed the ice problem, or specifically the albedo effect of the ice problem. And even the 3D models predict about a quarter of the surface or so is for early Mars, they predict could have been covered in ice for these icy Mars scenarios. And if you have that, you could probably decrease just the surface temperature itself by 10, 15, 20 or more K just from that. And more than that if there's more ice cover, and this ignores the atmospheric collapse and other issues. In contrast, I think, it's easier. Some people say it's icy is easier. No, I think it's actually easier to warm. If the planet doesn't have a lot of ice, it's easier to warm it up. So you need less greenhouse gas to warm the planet. Easier to satisfy the paleo pressure constraints. And so, I think that just makes, and you don't have to come up with a mechanism, try to explain how things can be transiently warmed various times. So these are arguments, again, we made in our paper. The 3D results also kind of confirm this. They confirm this ice problem as well. They get a somewhat mitigated temperature decrease because of CO2 clouds that partially mute the surface albedo. But if you want to warm early Mars, I think even, in recent studies, I think we are all in agreement that at least the recent work suggests that you need additional gases in addition to CO2, like methane and hydrogen or hydrogen to warm early Mars. The issue with methane in this case, if you add methane to a CO2 atmosphere, it heats it up. It heats up the upper atmosphere preferably. And you get these large stratospheric inversions. And what's interesting is that the CO2 clouds get wiped out, basically, largely reduced. The CO2 condensation, the upper atmosphere a good fraction of it goes away. So this muting effect that happens in a pure CO2 atmosphere would be a lot less pronounced in an atmosphere with methane. You'd have less CO2 clouds, and so the ice albedo problem would be greater in that case. And also, even in a CO2 hydrogen atmosphere, photochemical models predict you should get significant methane as well. So this will also occur where you'll have reduced CO2 condensation in the atmosphere. And I ignored in this discussion, the thermal inertia of ice, which can, worsen the ice problem in addition to the albedo effect. So methane actually exacerbates the ice problem for Mars. And so if you're going to invoke that, then this is something that the models will have to deal with to try to explain a warm climate. So my assessment really, when it comes down to it, is that early Mars probably had a warm, semi-arid climate for some time, maybe tens of millions of years, 100 million years or so. The rest of the planet may or may not have been, cold or coldish, but in the regions of valley network formation, I would expect that the climate was warm, and you had, warm enough to have surface liquid water, and that these regions may have shifted over time because there seems to be a temporal variation in when these valley networks were formed. And all of this is also consistent. If you have a semi-arid climate that's not that wet, you would not expect to have, wet-based glaciation or really thick glacial features forming after the end of this warm period. You would exactly what you would see. What you see is that there's little glacial evidence from this period. So it's against an icy scenario, but it's also against a very super warm Earth-like scenario, because you would expect glaciers to be thick if after the warm period and things cool down, but you don't see that. But if it's a semi-arid climate, then this would not be a problem. Even if you had thin ice accumulations from time to time, seasonal ones, they would rapidly melt. So that would not be an issue. So we think that this is consistent. A warm and semi-arid climate is consistent with the geological and climatological evidence for early Mars. In addition, then, so what does all this mean for exoplanets? I talked a lot about methane and ice. Methane's ability as a greenhouse gas is highly dependent on the spectral class. So, I just showed earlier in an earlier plot, mentioned how methane can warm early Mars slightly. It has a warming effect and an upper atmospheric absorption that occurs in the upper atmosphere. For M stars, the SED, or the stellar energy distribution, is kind of shifted to the right. So this is actually the spectral range where methane absorbs the best. So methane's going to absorb immediately once it gets that starlight up in the upper atmosphere around M stars. And we'll get these huge stratospheric conversions, even greater than that for the sun. But what happens is that there's so much energy being absorbed in the upper atmosphere that there's a lot less reaching the surface. So methane actually cools planets around M stars. So it's an anti-greenhouse gas. And whereas it's a greenhouse gas for warmer stars, which is kind of crazy, because even if you don't have hazes forming on M stars, this cooling will happen regardless. So, to wrap it up, if you add methane, the Hubble zone expands for hotter stars, say about 4,500 K, but for cooler stars, late Ks to Ms, it kind of shrinks it. And we've come to the conclusion that abiotic production mechanisms, if you have a dense CO2 methane atmosphere around a hotter star, or around these stars, it's probably going to be the planet is probably inhabited, because we did our calculation and there's no way you can produce such high methane amounts for these atmospheres with volcanism or serpentinization. So it's like a direct actual prediction that we can make. Whereas such atmospheres around cooler stars, since they're going to be frozen, the methane actually will cool these planets down. We can make a prediction that they would be just ice balls, which may or may not have life. We'd have to confirm that, but we can test these observables. So it's interesting predictions we can make from this theory. So I'll just leave my conclusions there. And I just wanted to say one more thing. Thank you for having me, and I'll glad to have any questions. Take any questions that you may have, and any students that are interested in possibly working with at ELSI, just see me after my talk at some time. So anyway, that's enough, and I'll be glad to take your questions.
We have a couple minutes for questions.
Hi, Ramses. Yeah, so we've published probably half a dozen papers over the last 5 years or so, explaining in painstaking detail why it's easier to achieve transient warming mechanisms on Mars than a permanently warm and wet climate. I suggest you go and read them again in more detail.
I disagree with you totally. I mean, I think we've refuted all that in our recent review paper. So but I invite you to read that one.
When you're using 1D models to assess surface albedo effects, you're neglecting the effect of clouds, you're neglecting a whole host of processes which we've already shown in the three-dimensional models makes this process not important.
The point in this talk was that your models were just used, the Forge et al. 2013 paper, for instance, only looked at pure CO2 atmosphere. They did not assess CO2 methane.
You have to use 3D models to understand the climate. The topographic effects are
don't
such
actually,
that
because for a warm early Mars, it's optically thick, and the heat transfer is very efficient. Actually, the 1D models and 3D models...
You're welcome to take our model and use it if you want to test these results, but it's not sufficient to do 1D modeling and make these claims.
Disagree with themselves, so,
We can talk about this afterwards. I just wanted to make that point clearly.
I'd love to take you up on that. So.
Yeah, let's maybe continue this conversation later. I see a question over there.
Hi. So I really thought it was interesting about how methane acts as a cooling agent on M stars, but as M stars also regularly turn into A stars, how would that affect the methane as a coolant in the atmosphere?
For A stars?
Yeah, M stars regularly turn into A stars during flares. So.
Well, that's a good question. For A stars, if you have an A star, I think we can go back to the slide here. I just showed F and G and M, but it's also true for the A stars that you would have a weaker stratospheric inversion in this case. So in that case, methane would tend to be more of a greenhouse gas rather than an anti-greenhouse gas.
Yeah. So I was just thinking, like, during large flare events, like, it could alter the effect on the planet, and so it'd be just really interesting to know, like, what the balance would be between the standard behavior and the flared behavior?
Well, that depends on how active the star is. So that would depend on the details of the star. But that's a good question. Thank you.